Now our last example is going to be a real life scenario of damped oscillations. We've got a guitar string. We know that when you plug a guitar string, it doesn't last forever. So we're going to look at the function that we can relate the frequency of sound we would hear from the guitar string, uh, or really the vibrations that the guitar string would cause. Um, and we're going to use this formula that can be attributed to either sine or cosine. Cosine's used when the um, time begins whenever you're at maximum displacement. So because we're starting when the guitar string is plucked, we're going to use cosine. If the guitar string had been at zero at time zero, in other words, the guitar string was just still at time zero, we would then use sine. So in this equation, k is going to represent our amplitude, or the distance displacement that the string or whatever object we're looking at has been displaced, which would be 0.95. Um, the Then we have times e to the negative c. Negative c is the damping constant, which they give us is 1.3. So we'll put in negative 1.3. T is our variable that the function is defined by, and we're going to use cosine. Now, omega is going to be represented by how many cycles are per second, the frequency. But what we have to remember is that omega is going to be divided by 2 pi, and that's what gives us our frequency of 200. So, because if you recall, the period was 2 pi divided by this variable that's multiplied, or this constant that's multiplied by this variable. So when we multiply that out, omega is going to be 400 pi. So we're going to have 400 pi times t, and that's one function that can represent this situation. Now, in the second part of this problem, we're looking at how long it takes for the string to be damped down to essentially 0.38 centimeters. We want our y value to be between the negative and the positive of that. So let's bring back our function so that we can then put it into the graph. So if we have y is equal to 0.95 times e to the negative 1.3, we'll use x power, and then that's times the cosine of 400 pi times x. Let's go ahead and try the trig fit. And that's probably going to be a little too much for our purposes. So what I actually did here was I zoomed the window in such that my maximum y value was at 0.4 and my minimum was at negative 0.4, so that when I look at the graph, I can see around where it actually fits into that window. So when I trace this, let's see here, it looks like it's about around this area where, we're getting that max of 0.38 and that min of 0.38 here. So it's somewhere in this area where we're going to hit that y equals 0.38, which appears to be at x equals 0.7 seconds. So that's what I'm going to say. The amount of time t appears to be roughly 0.7 seconds. So that's how you can figure out how long it takes to damp to that level. So see if you have a handle on that equation and see if you can come up with a model that represents this situation.